Hi everyone. We are now going to take a look at Chapter 4's information on discounted cash flow valuation. If I can get my screen to advance. There we go. So really what we're looking at in this chapter is a fundamental finance principle or concept regarding interest, which is very important for future calculations we will be doing in the semester. So we're going to be looking at the difference between what we call compound and simple interest. And we're going to describe and compute the future value and or present value of a single cash flow or a series of cash flows. So we're going to show you how to do those computations. And if you have a finance calculator, so I have a Texas Instrument TI-83 Plus, or if you have a TI-84, you may want to grab it because we could do calculations right on our finance calculators, or just to have a calculator nearby would be great. Also, you could do these calculations in Excel. So if you are familiar and feel pretty confident in Excel, these formulas are all right off our formula bar. We're going to define and calculate the return on an investment, and then we're going to recognize and compute the impact of compounding periods on the true return of stated interest rates. So when we are finished with this chapter, you will be familiar with all of these different concepts and skills. Further, we're going to develop facility with a financial calculator and or spreadsheet, there we go, to solve time value problems. Comprehend and calculate time value metrics for perpetuities and annuities. And finally, familiarize ourselves with loan types and what we call amortization. So we've got a lot of stuff packed in this chapter. So there's our outline, how we'll attack all those concepts and skills. So let's begin. So we have to start with this essential premise, and that is a dollar today is more valuable than that same dollar to be received in the future. Why? A dollar today is more valuable because it can be invested to make more dollars. It can be immediately consumed, and there's no doubt about its receipt. Okay, so I always use the example. When I was young, I would go to the store, the little corner store, family store, whatever you want to call it. This was in the 1970s. That was on our block. We didn't run to Sheetz or Turkey Hill. You know, we ran to Chidoba's, which was the little family market. And my mother would give me 50 cents and tell me to go buy a loaf of bread. So I was like 7, 8 years old, cross the street, go up to the store, and buy a Sunbeam family ranch bread. Now that is still sold today. It's one of the bigger loaves of bread. It costs 45 cents. So $1 in like 77, whatever it was, 76, bought 2 loaves of that bread. Fast forward 40 odd years. Sorry, I'm outside recording this. My dog is not happy with something. Clancy. But fast forward 40 odd years, that same $1 doesn't even buy a loaf of bread. So that's what we're saying here. That's how you have to look at a dollar. So if you know your required rate of return, so what percentage you want to make on a dollar, and the length of time before you'll take the cash out, or I like the way they put it, before the cash is harvested, you can calculate some critical metrics related to your money. And the value today of a payment to be received in the future is called present value. So we need to define some aspects of our calculation. So we say time zero value. That is right now, today. It's not the beginning of, it's not January 1, it's today, whatever today is. Then we want to calculate that money to a value in the future. Well, that future date, okay, will tell us the future value. So it's the value on a future date. Now, we can calculate both, but we need to be given certain variables in order to do that. So that's what our first part of our discussion is going to be on. So let's look at an example. If you were to invest $10,000, say in your savings account, at a 5% interest rate for 1 year, what would you have at the end of the 1 year? Well, today, you have $10,000, so that's your present value. The end of 1 year would be the future value. You also need to know the time period you're going to invest that money at. So it's 1 year, and the interest rate that will be used to calculate your return on your money, and that's the 5%. And since the time period is 1 year, we're going to use the annual percentage of 5%, the entire amount of it. So $500 in interest would be earned, or $10,000, what you're investing, times your rate of return, 5%, $500. So what this formula calculation is doing is showing you, okay, today you have 10,000 present value. What will you have in the future? You will have that 10,000 times that 10,000, which is 100%, plus 5%. So 1.05. So at the end of 1 year, your future value equals present value times 1 plus the interest rate, or 105% of 10,000. So the total amount due at the investment, again, is the future value. So now we can create a formula and calculate it for any numbers. So we could have 20,000 at 6%. So if you grab your calculator, present value is 20,000 times 1.06. So the future value of 20,000 invested today at time zero present value times 100%, because you're still going to have that 20,000, but 100% plus 6%. So 1.06, 21,200, the future value. Whoops, sorry about that. I'm hitting all kinds of keys on my laptop. I don't have my mouse or my keyboard outside. So there it is. There's our formula. CO is your cash flow today, or present value. So you could use PV there. It means the same thing. Cash flow at time zero. Your investment at time zero. Times 1 plus R, your interest rate. Now, what if you know what you need at the end of 1 year, and you know how much interest you can earn, but you got to find out, well, how much do I have to put away today at time zero to have this much money in the future, $10,000, when that money is going to be earning a 5% interest? Well, to define it, present value. So what we're trying to figure out is today's value of an amount to be received in the future, given a specific interest rate and time horizon. So how many years, or how many months, or how many whatever. In our case, we're staying very simple, 1 year. So suppose you were promised $10,000 in 1 year when the interest rates are 5%. How much would you have to invest today, or what would your investment be worth at time zero? Well, if you take the $10,000 future value and divide it by 1 plus the interest rate, or 1.05, that will give you the present value. So all we did was algebraically move around the original formula that was future value equals present value times 1 plus the interest rate. So now our new formula to calculate present value would be future value divided by 1 plus the interest rate. And there it is. So they use future value as the cash flow at the end of year 1 divided by 1 plus the interest rate. Net present value. Net present value. This is used to determine whether you should, or a company should, get involved with an investment opportunity. Maybe it's buying equipment or building a building. The net present value of an investment is the present value of what we call the expected cash flows from it, less the cost of the investment. So here's an example. Suppose an investment promises to pay $10,000 in 1 year. So it's going to pay $10,000 in 1 year. It's offered to you today to buy for $9,500. Should you buy it? You just don't go, oh, well, I'm going to get $10,000 at the end of year 1 and $9,500, I only have to pay for it. Yeah, I'm buying it, I'll have $500. No. What you want to see is, what's the present value of that $10,000 given that 5% interest rate? So what you do is, you say $10,000 divided by 1.05. So the present value of that future $10,000 payment is $9,523.81. So that's what you would pay for that investment to truly get $10,000. How much are you going to pay? $9,500. So what we do with net present value is we say, we compare today's value across all the cash flows from that investment. So if you're going to pay $9,500 today, you're going to expend or negative $9,500. What are you going to receive in the future? Oh, $10,000. Well, to truly see, should I pay $9,500 for that, you have to see what's the value of that $10,000 in terms of today's dollars, $9,523. So since this is a positive result, you're only paying $9,500 for something that really has a value today of $9,523.81. You would buy it. So we use present value to determine if we should invest in different things in our companies. So again, net present value equals the cost of something today plus the present value of the future cash flows from it. So if we had not undertaken a positive net present value project considered on the last slide and instead invested our $9,500 elsewhere at 5%, our future value would be less than $10,000. So 9,500 times 1.05, that future value would only be $99.75 when we could have invested in something that 9,500 and received 10,000. So you can look at it from these two different perspectives. But to do the actual computation, we take the cost, and that's always subtraction, a subtraction because you have to expend that money, and compare it to the cash flows, what we call discounted back or stated as present value amounts, not future. Whoops, I keep doing this, sorry. Hitting the wrong thing. Okay. So that was pretty straightforward. Starting simple. Now, what happens if our future value is more than 1 year, or what we say multiple periods of time? What we calculated in those first few slides was simple interest for 1 year. And basically that says interest rate times your principal times 1 year is your interest. But what if we have more than 1 year? So if it's a simple interest calculation, all interest is calculated on the original amount. Okay, so suppose an investor has $1,000 to invest at an interest rate of 9%. In 1 year, they will earn $90, just like we did before. With simple interest, you will only calculate the next year's interest on the original investment. So always the 1,000. But that's not how we compute interest in the real world. Okay, let's go. We use instead what's called compound interest. That's truly how interest is calculated. What does this mean? Interest after the first year is calculated on original principal plus interest earned to the beginning of that period and part of that investment. So suppose an investor has $1,000 to invest at an interest rate of 9%. In 1 year, they will earn 9%. But the next year, their interest, the second year's interest, won't just be calculated on $1,000, but $1,000 plus the $90 from the first year's interest, $1,090. So the second year's interest will actually be $98.10. $90 on the 1,000 and $8.10 on that $90 of the first year's interest. So that's what we mean by compound. It's not going to just, interest is not going to be earned just on the original principal, but the original principal plus all interest earned to the beginning of that period that we're calculating interest for. So that's okay, we'll keep going. So how do we calculate this? So now we're kicking it up a notch here. So the first way we can calculate multiple years value is for future value. What does this mean? Think of it as you're going to put $10,000 into a savings account. It's going to be invested for 5 years and make 3% interest each year, and it compounds each year. That means interest is calculated on whatever's in the savings account as at the beginning of that year, and then added to that balance. So we could use a formula, and there it is. It's very similar to what we used a couple slides ago for future value. Future value equals our cash at time zero, or what I call, and it's called present value. Just not me, everybody calls it that, times 1 plus your interest rate for your compounding time, to the T power, or the number of periods you're going to hold the investment until the day you want to know its future value. So let's take a look. Suppose the stock currently pays $1.10 in interest or dividends, which is expected to grow at 40% per year for the next 5 years. What will be the dividend in 5 years? So today, the dividend is $1.10. So present value is then multiplied by 1 plus the return, 40%. So 1 plus 40% is 1.4 to the 5th power, which is 5 years. So on my calculator, I'm going to take 1.4, and I have like a little carrot top. It's over on the right side of my TI-83 underneath the clear button. That's how I'm able to raise to the power. So whatever calculator you're using, you want to either read the directions that came with it, or Google it, or and see how to raise to the power. And that result is 5.37824. Now multiply that by the $1.10 present value, $5.92. And it doesn't come out exact, so you have to round because they're asking for a dollar value. Okay, so notice the dividend in 5 years is $5.92. It's considerably higher. Why? Because it's growing each year by 40%, okay, and compounding as it grows. So there's a great picture of what's actually happening there. So the first year, you're taking 1.10, that's your value. Then the next year, 1.10 times the 1.40. Then the $1.10 times 1.40 to the second power, third power, fourth power, and then you can see the fifth power. So that's its value. I love timelines when we're working on these. Times 0, future value at the end of 5 years. You can also do this with present value. So here's your formula. You take your cash flow at the future value, they call it CT, I call it future value, divided by 1 plus the interest rate, or the rate, raise that to the number of periods power, or years right now. Now first do your raising of the 1 plus R to the 5th power. Take that result and divide it into your future value, CT. And that'll give you the value of that item today, present value. So take a look. How much would an investor have to set aside today in order to have $20,000 at the end of 5 years from now if the rate is 15%? Well, remember what I said. Your formula says take 20,000 divided by 1 plus their rate to the number of periods power. So it'll be 1.15 to the 5th power. Get that result first, and then divide that into the 20,000. 20,000, and I get divided by 2.0 114, I'm just going to round it, 9,943, and it's off a couple cents because I didn't use the entire result. If I did my 20,000 divided by 2.011, 357,188, 9943.53. So I suggest you do that as many places, decimal places that your calculator gives you, use all the numbers. Don't round. Now, you've seen the formulas. We have always been given the time, the interest rate, and either the present value or future value. But what you have to keep in mind is you can solve for any of these as long as you have 3 of the other items. Okay, now the math can become cumbersome, and as they said, financial calculators and spreadsheets can be very helpful. But let's take a look. If we deposit $5,000 today in an account, paying 10%, how long does it take to grow to 10,000? So we know our present value, 5,000. We know our future value, 10,000. So what we would need to do is, first of all, put that into our formula. 10,000 equals 5,000 times 1.10 to the t power. We're solving for t. Now, the beautiful thing is that when you have calculators, you can easily solve for t. Let's see, 1.10 inverse log. I haven't done this in a while. All right, the log of 1.10. There we go. And it's off a little bit. Okay, how do we solve for it? We have to take the inverse of 1.10 to the t power, which would be inverse of 1.1, and divide that into the inverse of 2, which, let me just see something. My numbers are a little different. I may not be using the proper, let me see. Oops. Just give me a second. Okay, guys, sorry. I was reading this incorrectly. I knew what I had to do, but I couldn't figure it out on my calculator quickly, and I wanted to take some time to look it up, so I make sure I explain it to you. That I'm calling it IN. It's ln, which is a natural log, and you should have that function on your calculator. It's been a couple of years since I took some more advanced math to remember all the algebra and trig and all that fun stuff behind our calculations. But ln, natural log, which would be ln on your calculator. On my TI-83, it's on the right-hand side, right column, probably about the 5th one down. So to get the number of periods that would be required to invest this money. Sorry, I'm doing 2 things at once here. It's not the perfect recording. Okay. We would continue down. 10,000 divided by 5,000 would give us 2. To find our t, or number of periods, we would take the natural log of 2 divided by the natural log of 1.10. And that would give us, as you can see, 0.6931. So on your calculator, natural log ln 2, enter 0.6931. Natural log ln 1.10, enter 0.0953. Finish up your math there, and you can see 7.27 years. So The point of this is that you can calculate any of the variables as long as you have the other three. Take a look at the next. Assume the total cost of a college ed will be 50 grand when your child enters college in 12 years. You have $5,000 to invest today. So the assumption is you're only going to invest 5,000. You need it to grow to 50,000 in 12 years. So the question is, what kind of return do you need on that money to reach that goal? So you know the future value divided by the present value, 50,000 divided by 5,000 equals 10. 10 to the 1/12th power will give us 1 plus r, 10 to the 1/12th power. Okay, so the first thing that I do is take 1 divided by 12, and then I raise 10 to that power. 10 to the 0.0833333 power gives me 1.2115. But remember, that number is 1 plus r. So we would have to subtract 1 from that. Your answer would be 21.15%. So we saw solving for present value, future value, for number of periods, and for rate. Now, if you're using the Texas instrument, one of the different calculators, again, if you have, one that's not Texas instrument, or you're not finding these keys we're talking about, you need to consult your own instructions or Google it. There's many people put out on YouTube videos, trust me, on using these calculators. I didn't grow up on these calculators. You guys have it much easier as far as calculations go than I ever did. But in my calculator, my TI-83 and TI-84s have these. You should have an apps button. Mine is blue and it's in the second column, about the third one down. And when you click on that, it'll give you different applications. And I'm going to select finance because we're doing finance calculations. And then I'm going to use the TVM solver, which is my item 1. So I'm just going to click 1. And then you can see all of our variables are listed there. N is the number of periods. I% equals the interest rate or the rate. PV equals present value. PMT we will talk about right now. You don't need to, just make sure that's 0. FV, future value. P/Y stands for periods per year. C/Y stands for compounding per year. I'm sorry, payments per year is the P/Y. C/Y is compounding per year. Those should be 1 right now. And then PMT, you'll have the words end or begin. Now, those will make more sense in our next discussion. But for now, if you wanted to calculate number of periods, you could either use the formula or use your finance calculator to do that. Okay, so take a look at your instructions and see which one works best for you. Now, consider an investment that pays $200 1 year from now, with cash flows increasing by $200 per year through year 4. If the interest rate is 12%, what is the present value of all of that money? If the issuer offers you this investment, you paying $1,500 up front for $200 1 year from now, and then increasing by $200 each year through year 4, should you purchase it? Now, there's not a simple calculation necessarily for this, because you are going to be receiving or looking at an increase in that future value each year. So what you want to do is say, okay, at the end of year 1, how much money will there be? Future value. What's the future value of the next payment, which would be $200 more, or $400? And then the next payment would be $600. and then the next one, 800. What you would need to do is calculate what the value of those payments, future payments, are worth today. So you would take future value divided by 1 plus the interest rate of 12% for year one, 178.57. Now take future value 400 divided by 1 plus the interest rate of 12% to the second power, because that would be at the end of year two. So divide that by 400, the future value. So I got 400 divided by 1.2544, $318.88. For the next one, you would take 600 divided by 1.12 to the third power, 427.07, because the future values at the end of each year are increasing. The last one is worth 800. Divide that by 1.12 to the fourth power, the end of 4 years. So what we're doing is trying to figure out how much each of those future payments that we're being promised are all worth today. So individually, we calculate them and then add them all up. So the present value of those future payments is $1432.93. So that should be the amount of money we pay for them. Since the cost of them is greater than that, you don't purchase it. You find an investment that will be more than the present value of $1,500 to buy today. What if you have uneven cash flows? For instance, you have, oh, that's what we're talking about there. This is using your calculator. So valuing your uneven cash flows in your calculator, again, you would need to read the instructions on your calculator. I can't go through all the different calculators in our discussions. But quite honestly, with my calculator, I've never used the uneven cash flow. Just looking to see if it's, yeah. I'm sure I have that ability, but I've never used it. So it gives you a demonstration here on how you can do it. You could use it with net present value, it looks like on my end. Enter. Yeah, you have to put it in as a formula. So you could do it through your calculator, or you can do it the way I just did it, through that old-fashioned simple formula with math, and you could draw yourself a picture as well. So all examples this far have assumed annual compounding. And I already saw on the discussion board, some people are like, oh, this thing, when it's more than once a year, it's confusing me. Don't let it. So sometimes banks will compound interest on investments quarterly, sometimes monthly, like our loans are monthly, or even daily. Mortgage companies compound interest monthly because we make monthly payments. However, and it's actually a law in the United States that interest rates have to be expressed as annual amounts. So there's a problem, not problem necessarily, but an issue, I guess you could say, with our calculations. They're not as straightforward if interest is compounded more than once a year. Because here's what happens. Your interest rate is stated in an annual rate, 10%. But the assumption there is, and you would only use 10% in your calculations if it compounds once a year. What if the interest compounds quarterly? Well, if interest compounds quarterly, what you need to calculate is an interest rate for each quarter. So you would take 10% divided by 4 quarters. The interest rate per compounding period would be 2.5%. So that it's 10% for the whole year, but 2.5% each quarter, not 10% each quarter. What if the interest is compounded daily? 10% divided by 365 days. Your interest rate, let's see, 0.2 divided by 365. Whoa, yeah, it's not even giving me. It would be about, I think, 0.27% per day. What if it's compounded semi-annually twice a year, divided by 2? The interest rate each compounding period, and that's what we use in our formulas, is the rate for each compounding period is 5%. So this leads us to this concept or this calculation of what we call effective interest. Compounding an investment M times a year for T years provides for the future value of wealth. All right. So how do we calculate our investment amount when we compound more than once a year? Well, the first thing we do is we use our formula. Future value equals present value of our investments, or cash flow at times 0, times 1 plus the rate for the compounding period, which your author defines as R, the annual rate, divided by M, the number of times it compounds in a year. So R, 10%, if it's quarterly compound, divided by 4. So 1 plus 2.5. Raise that not to the number of year power, but the number of compounding periods, which would be the number of years of the investment times the number of compounding periods per year. So if you compound for 4 quarterly, 4 times a year, and you're going to keep it invested for 3 years, the number of periods it compounds is 12. So that's what that formula means. So if you invest $50 for 3 years at 12%, and it compounds, and that just means interest is calculated twice a year, your investment will grow to, take a look, present value is 50, times that by 1 plus your compound interest rate, which would be 12% annual divided by 2, or 6%. Raise that not to the 3-year power, but the number of compounding periods power. 2 times 3. Now, we didn't have to do this before because our investments compounded annually. But if they compound more than once a year, we need to convert our interest rate into a compounding period interest rate by dividing it by the number of compounding periods per year. And we need to, or the number of times it compounds a year, I should say. And we need to change our number of periods it compounds from annual by taking the number of years times the number of compounds per year. And that's what M represented. And you could see what our answer would be. So because we may compound more than once a year, our effective annual rate, how much interest we really do receive, is going to be different than our annual rate that is stated. So that's 6% or 12%. What is our effective annual rate of interest? So it's the effective annual rate, or EAR we call it, is the annual rate that would give us the same end of investment wealth after 3 years. So we could create a formula by saying it's the present value times 1 plus solve for EAR to the number of years, 3 powers equals 7093. So what we would do is exactly what you see there. Take 7093 divided by 50. So we're just using our algebra here. Take, we'll flip over our, not flip over, but flip over really the to the third power to the 1/3 power. So we would take 7093 divided by 50 and then raise that to the 1/3 power. So I just take 1 divided by 3. So 1.41, whoops, 86 times, or I'm sorry, not times, hi-hat. I'm sure there's a nice, cute name for that, but I just call it the hi-hat. To raise it to the power, 0.333333 into infinity, right? And we get 1.1236. Now remember, EAR is found by subtracting the number 1 from that, as you can see there. So the effective annual rate is 12.36, and it is because we're just not compounding once a year. Since we're determining interest or compounding more than once a year, the amount of interest will increase. Why? Because after the first 6 months, we calculate interest from the beginning of the year's investment to the first 6 months, the end. We then add that first 6 months worth of interest to the beginning of the year's investment balance and calculate interest again. So in the end, we're earning more than 12% interest because it's compounding more often. So the interest rate we're truly earning annually is 12.36%. And that's what effective annual rate of interest is. So find the effective annual rate of an 18% APR, so that's your annual percentage rate loan that is compounded monthly. Now, what we have is a loan with a monthly interest rate of 1.5%, 18% divided by 12. This is the equivalent to a loan with an interest rate of 19.56%. How do we get that? 1 plus rate of return for the year, 18% divided by number of compounding periods per year, 12, to the number of payments for the year, 12 power. And you can see the rest there. We subtract 1 from 1.1956, and it gives us our annual, our effective annual rate. So they're showing you on your calculator some of the functions that you can use to do this type of calculation. I'm just looking on mine very quickly. If it be in my finance area or not. Yeah, there's principal, interest, nominal, effective. Yep. Looks like I have one. But mine's all in formulas. So you would need to, again, refer to your instructions or YouTube to see how your calculator can help you calculate the effective annual rate. But no, I learned these back in the 80s and the 90s when I was getting my master's degree, and we didn't have these fancy, great calculators we have today or Excel to the degree we have today. So these are really nice additional tools you have to help you calculate your answers more quickly. I always encourage you to use the formulas, though. You could use them as a double check. Okay. The next formula is for the future value of an investment that compounds continuously over many periods. And the formula for that is future value equals cash at time 0 times E to the R, stated annual interest rate, T, number of years. And E is a constant that is approximately equal to 2.718. E to the X is a key on your calculator. And I see mine, it is actually, I have to hit the orange second key at the top in the first column on the left, and then the natural log function. And let me go back to that. See if I can go back. Okay, so we're just giving you that formula there. Let me pause you a second. You won't even know I'm paused, but I'm going to grab your book. I don't think I have it out here with me. Nope. So let me find my pause, and I'll be right back. Okay, everyone, I'd like you to go to page 99 of your book, because we don't really have any examples of continuous compounding. And I want to take a look at example 4.14, just so you can see this in action. Linda DeFond invested $1,000 at a continuous compounding. So it's always compounding, continuously. And the rate she is continuously compounding is 10% for 1 year. What is the value of her wealth at the end of 1 year? So we're going to take that $1,000 times, and you're going to use that E to the X function on your calculator. So I'm going to hit that second button and the E, and then I'm going to put the interest rate in as 10. Now, if it was more than 1 year, it would be the number of periods times T, but I'm just going to put 10 in. Oops, I'm sorry, I should put in 0.1 as 10%, and you get 1.1052. So let's say it was 3 years continuous compounding. We would take the E to the X on our calculator times, it would be 0.1 times 3. Let me see if that'll let me do that. Yes, 1.3498. Then multiply that by her original investment, and it would be 1349.85. Okay, so just to give you a little flavor there for continuous compounding, and that's what the next one down does, but it takes you to 2 times a year. Or I'm sorry, 2 years. In 4.16, you can also determine present value. So the Michigan State Lottery is going to pay you $1,000 at the end of 4 years. If the annual continuously compounded rate of 8%, what is the present value of this payment? So remember, you can determine future value by taking present value times E to the rate and time power. Well, you can find present value by taking 1,000 times 1 over E to the interest rate, 0.08, times 4 years. So take a run through those and see if you have any kind of questions. The next, check something very quickly before I keep going. Okay, guys, so the next thing we want to look at are perpetuities, which is a constant stream of cash flows that lasts forever. So it's the same amount of money that at the same time period forever and ever and ever. A growing perpetuity is also a stream of cash flows, but it consistently grows at the same rate forever and ever and ever. An annuity is a stream of constant cash flows that only lasts for a fixed number of periods. A growing annuity is a stream of cash flows that grows at a constant rate for a fixed number of periods. So perpetuities last forever, annuities do not. They both can grow, meaning increase over time. So let's take a look at perpetuities. A constant stream of cash flows that lasts forever. So there's a picture of it. The present value, what is that worth today, can be found by taking the amount of the payment divided by the rate. So the amount of the payment divided by the rate. Come on, go to the next slide. There we go. So what is the value of a British consul that promises to pay 15, I guess, we'll just keep it as dollars, every year forever? The interest rate is 10%. Take the $15 divided by the interest rate of 10%. So what should you pay today to have the ability to have that payment at the same amount every year forever? $150. What if it's a growing perpetuity though? So now you start today with a certain payment, but each year it'll continuously grow at the same rate forever. The formula, how much should you pay for that ability to receive that growing amount each year forever? Take the original cash from today that you'll receive, that very first payment, divided by the rate minus the growth rate. Take a look. The expected dividend next year is $1.30, and dividends are expected to grow at 5% forever. If the discount rate is 10%, so that's like your interest rate, you could think of it, what is the value of this promised dividend stream? So $1.30, your first payment, divided by 10%, the annual discount rate, minus the growth rate, the constant growth rate each year, 5 cents, $26. So you should pay $26 for that stock that will pay a dividend that will constantly grow at 5% forever, or until you sell the stock. So you see how this calculation can help you determine investment decisions. Those were perpetuities. The next type of investment is something called an annuity. Now, a lot of people go, oh, annuities, that's what you get when you retire. No. Annuity isn't what you get when you retire. That could be what it's called sometimes. But what is an annuity? It's a word we use to describe. So it's just a word we use to describe a constant stream of cash flow. So normally, the same amount of money over the same time period. So every quarter, every 6 months, every month, every year, for a fixed period of time. So not in perpetuity. And there is our formula for calculating that. So what if we want to know what's the present value? So what are these constant payments, so the same dollar amount, monthly payments of $100 for 5 years worth today, assuming there's an interest or rate of 10%. We would take that constant cash flow, so it has to be the same amount each year for this one, divided by the rate, times 1 minus 1 over 1 plus the rate to the number of payments, T. And that's just showing you how that formula was created. I say just focus on the formula. So if you can afford a $400 monthly car payment, how much car can you afford if interest rates are 7% on a 36-month loan? So $400 is your constant car payment amount. Divide that by the interest rate. Now, 7% is an annual rate, remember. It will always be stated as annual, and that's the assumption, unless they tell you differently in a problem. So 7% divided by 12, first divide that out. Multiply that result by 1 minus 1 over 1 plus 07 divided by 12 to the 36th power, because it's a 3-year loan or 36 months. So you want the number of payments as that power, and you'll get 12,954.59. And just so we're aware, we follow through on the calculations. 400, I'm sorry, let's take 0.07 divided by 12. Then divide that result into 400. 400 divided by 0.00583333. Okay. Multiply that by 1 minus 1 over. So let's do the first one. 1 plus 0.07, which we know is 0.0058333. I'm going to raise that to the 36th power. I get 1.232924. Now I'm going to divide that answer I just got into 1. 1 divided by 1.232924,117. Subtract that from the number 1. 1 minus 0.8110799,247. Multiply that result by that very first one I got, the 400, and I don't even have it in my calculator anymore. The 400 divided by 0.07 divided by 12. That's not right. 0.07 divided by 12. So 400 divided by 0.0058333. And then I'm going to multiply that 68,571 by 0.1889200,753. And I get 12,954.59. Now, your calculators have a great finance function in them. It's the apps. So you go to your apps, finance, time value of money, TVM solver. So in that last example, my N was 36. My I was 8, nope, it was 0.85333. So it was 7% divided by 12. I'm solving for PVM, so I'm going to make sure that's 0 right now. PMT is the $400 for the $400 payment per month. And then I want to make sure loans you always pay at the end of each month. So where it says PMT with the words, I want to make sure the word end is highlighted and enter. Then I'm going to use my arrow keys to go back up, and you use the arrow keys that are, mine are in the top right. They're just arrows. And then I want to solve. And the tricky thing with the apps is that to solve on my calculator, I have to hit the green alpha and then enter. It looks like mine's a little bit different. I think I used the wrong interest rate. Let's go back over. Oops, that's growing. Let me go back. 1 second here. The growing annuity, we don't want that yet. Yeah, mine's off a little. Come on, Lori. From this side, okay. So I'm off a little bit because I'm going to exit or quit. Oh, it's 0.58333. Well, that would make a big difference. So my interest rate, I inverted the number, should be 0.58333. Then I'm going to arrow down and alpha enter, and I get 12,954. Now, if you're using your calculator, you're going to see sometimes numbers will come up, either present value or future value will come up as a negative number. It doesn't mean it's negative. When these calculators were designed, and Excel's the same way, in finance, we look at you're either putting money in and then taking it out. So going in, it could be positive, and then coming out negative, or vice versa. So it will show up as a negative. It doesn't mean it's negative. Now, what is the present value of a 4-year annuity of $100 per year that makes its first payment 2 years from today if the discount rate is 9%? Wow, that's a great problem. So again, we could use our calculator, and we're going to use our formula. I'm just going to grab the formula right in the book instead of going back and forth. Which would be, you would first take 100 divided by the rate. So it's an annual rate, and it's annual payments. Yep. So divided by 0.09. So 100 divided by 0.09. Then multiply that by 1 plus 0.09 to the 4th power. Divide 1 by that result. And then subtract that result from 1. 1 minus 0.87630 to 7196. Multiply that result by that very first C divided by R. And I'm getting something different than that. I think I did something. Let's try this again. Sorry about that. So I'm going to take 1.09, raise that to the 4th power. 1.41. 1.41. I'm going to divide that into the number 1. Oh, I subtracted it from 1. I didn't need to. 1 divided by 1.4115861. Sorry about that. Multiply that result by the C divided by R, 400 divided by 0.09, or 111.11. Okay. And still getting a little different number there, Lori. Give me 1 second, guys. See what I'm doing wrong. I apologize. You don't want to see me. Okay. Okay, sorry about that and the confusion there, but I was right in the beginning. So I'm going to take 400 divided by 0.09 times 1 minus 1 over 1 plus r to the t. So 1 divide it by 1.41158, which is 1.09 to the fourth power, will give you 0.708426. Subtract that from the number 1 to give you 0.29157. Then multiply that by your 400 divided by 0.09, which was 1111.1111. So after all of that, the present value of those 4 $100 payments received at the end of each year for the next 4 years would be $323.97. Now, it's saying, well, wait a second. That's your 4-year annuity. You're not going to receive that first payment until the end of year 2. Okay? So we need to know what's the present value today. Now that 323.97 gives you the present value as of the beginning of year 2, which is the end of year 1. Beginning of year 2, which is the end of year 1. And you can see it on your picture there. That's what it's telling you. That's the present value. But we need to know the present value as of the beginning of time 0, not the beginning of year 2, end of year 1. So we have to divide that by 1 plus the interest rate. And that will give you $297.22. So this is like they call this a deferred type of problem. And you really have 2 different calculations. So when you find the present value of this annuity, it is not the present value as of time 0. It's the present value as of the beginning of year 2, which is also considered the end of year 1. So be careful of that. Sometimes an annuity will grow at a constant rate, but still only have a fixed number of payments. So look at that calculation. Now that's getting nice. Present value. So what are those future payments that will grow constantly, but have a fixed term worth today? So it'll be your amount of your payment each month, each year, whatever it may be, divided by your rate, interest rate minus growth rate. Divide that R minus G into your payment. Multiply that by 1 minus 1 plus G divided by 1 plus R to the number of periods power. Wow, let's take a look. A defined benefit retirement plan, which if you're not aware of, a defined benefit plan means no matter how much money you put into your retirement, you're promised a certain amount at retirement. So this plan offers to pay $20,000 a year for 40 years and increase the annual payment by 3% each year. So your first payment, $20,000, then you're going to get an increase of 3% of that $20,000 for the first year, then that result times 3% for the second year, etc. What is the present value at retirement if the discount rate is 10%? So we have all of our factors there. The amount of the payment each year is $20,000. We'll divide that by the interest rate minus the growth rate. So 10% minus 3% or 7% divided into 20,000 will be $285,714. We'll multiply that by 1 minus, and first we'll determine 1.03 divided by 1.1. So 1 minus the 1 plus the growth divided by 1 plus the rate. That result is raised to the 40th power. Now subtract it from 1. So 1 minus 0.7207. Multiply that result by the 285,714. And you get 265. And because I did some rounding, it's not exact, but I got 122. So we just use the formula. Okay, but it shows you in the previous slide how that formula is determined, and here's an example of how we would use that. So again, perpetuities can be fixed amount forever, or a fixed amount that, or I should say, an amount that grows at a constant rate each year, but the payment is forever. Annuities are different. Annuities are a constant amount that are paid during a fixed period, or an amount that constantly grows for a fixed period of time. So those are our different ways of calculating annuities and perpetuities. The next area are different types of loans and what we call loan amortization. And this, you can go and grab one of your loans and do this right now if you wanted, right after you finish listening to this. There are what we call pure discount loans. These are your simplest form of a loan. The borrower receives money today and then repays a single lump sum, all principal and all interest at a future time. Very, very simple. Interest-only loans, these are like construction loans, require an interest payment each period. So if you ever built a home, or if you're ever involved with building a home, construction loans are given while you're constructing your home. And as you take money to pay your contractors, you will pay interest only on that. And then when the construction loan is done, you pay off the entire principal you borrowed. But really, you just convert it, that principal payoff of construction loan is really you converting it into a mortgage. Which brings us to our next type of loan, and probably the most common type, amortized loans. You repay principal and interest each payment. Principal and interest. So what you originally borrowed plus your interest is paid each payment. So here is an example of a pure discount loan. Treasury bills are an excellent example of them. The principal amount is paid at some future date, but there's no periodic interest payments made at all. So if a T-bill, a treasury bill, promises to repay $10,000 in 12 months, and the market rate is 7%, how much will the bill sell for in the market? Well, it's going to pay a future amount of $10,000. It's only going to pay this amount in one payment in 12 months, so 1 year, and the annual interest rate is already 7%. So divide that by 1.07, 1 plus the interest rate, the 10,000 future value. How much should you pay for it, or how much will it sell for? Its present value today, $93.45.79. So you can now see how we incorporate present value into loans. What about interest-only loans? Well, consider a 5-year interest-only loan with a 7% interest rate. Principal amount is $10,000. Interest is paid annually. So each interest payment date, the end of the year for the first 4 years, the person will pay $700 of interest only. But the year the loan matures, the person will pay $10,000 principal plus $700 in interest. So you would just take principal times interest rate, and since this is an annual payment and an annual interest rate of 7%, your annual interest will be $700. And we will be using this type of calculation, I believe, in our next chapter. Whoops, make sure I'm sharing this with you guys. Okay. All right. Let me make sure. Sorry, I don't want to be talking and not be sharing this screen with you. So, okay. Oh, come on. Give me a lot of problems today. Sorry about that. Okay, let's look at some amortized loans. So we have amortized loan with fixed principal payment. So they're actually going to use Excel here to demonstrate this. And I'll talk you through what they did. Consider a $50,000 10-year loan at 8% interest. The loan agreement requires the firm to pay $5,000 in principal each year plus interest for that year. So I'm going to double click on this. There we go. And I'm going to make sure that you're actually seeing the Excel screen. So here is the, oh, come on, I want to lift it up there for you, answer. And what you see in front of you here is something called an amortization schedule. First column, that is the beginning balance of the loan for the period or the row we're looking at. So in year one, before the first payment is even made, the beginning balance of that loan is $50,000. What we'll do is calculate interest on that $50,000 for the year. So $50,000, and if you look up in the cell, the bar, the formula bar up in the top, we take the cell reference that the 50,000 is in, B2, and multiply it by 0.08. So this could all be done through formulas very quickly. The principal payment is constant each year, $5,000. So the first year, the total payment, principal plus interest, $9,000. But you have to remember that you just paid off part of that $50,000. So the loan balance has decreased to $45,000. So when we go to calculate year two, you're going to start with a beginning balance of $45,000. Multiply that new principal times 0.08, 8%, to give you $3,600 of interest. Principal payment will be $5,000. So the total payment for year two is $8,600. But now your principal of your loan is down to $40,000 because you paid another $5,000 off. And you can follow those numbers down through this Excel sheet and see that as the loan gets older, the interest will decrease along with the principal because you'll be calculating interest at a lower principal amount. So that's a great Excel sheet. And if you go back and you want to grab this Excel sheet, you can see that on the principal payment column, $5,000 is constant. But take a look at the total payment. It adds the amount in cell C3 to D3 to get total payment in E3. And then it takes the amount in B3, which was the beginning principal, subtracts the $5,000 payment in D3 to get the ending balance. And if you know how to copy these formulas, you could just now copy everything down and it'll automatically calculate for you. So practice that a little bit if you're interested in Excel. So I'm going to stop sharing that and go back over to my PowerPoint. We're getting near the end. Okay, let me go to the next one. Amortized loan with fixed payment, Excel example. So now this is going to differ. This isn't, let's see. Yeah. This is going to be where our payment is going to be part interest and part principal. But the key here is that it's a fixed payment. It doesn't change as interest changes or principal changes. It's here's how much you're going to pay each month, each year. Part of it will pay interest, part of it will pay principal. So the first obstacle, I guess, you have to overcome, if you don't know that fixed payment, you have to calculate it. So here's how you do that. It's really an annuity problem. But if I use my apps button on my calculator and I go to Finance and TVM Solver, N is 4. Interest rate is 8. PV is 5,000. Now I'm going to go hit one more arrow down, and I'm going to be in the PMT, and I'm going to solve, alpha, enter, and I get 1509.60. Now, if you're like, well, I don't really have that calculator, I don't know, you have to fit these amounts into your present value of an annuity formula so that you can solve for C. That's how you would have to determine how much this annual payment is. So that's the first step. The next step is then let's create an amortization table to determine and show you how much of that 1509.60 is for principal, how much is for interest. So if you currently have a loan that you know how much you originally borrowed, you know the interest rate, and you know the payments, the number of payments, okay, and you know the amount of each payment, you can create one of these amortization tables. Trying to get to Excel, come on. Maybe it'll do it for me this time. There we go. So I'm going to make sure you guys can see this. Go into sharing, Excel. Sorry, I'm going to have to. Oh. Sometimes technology does not want to agree with me, so just hang in there with me, guys. There we go. Now let me stop sharing and reshare this. There we go. Okay. So now what you see, no, that's not what you see. That's the old one, isn't it? Trying to get this one. Come on. There we go. I got it finally. No. Oh, they mustn't have updated it. Well, I will create one very quickly, unless I'm on the wrong slide. No, that's the wrong one. Okay. Hang in there with me, and I'm going to go over to Excel and create what it will look like. All right. So our loan amount was $5,000. I don't know if it's going to let me change that, so let me go to a new screen. There we go. All right. So we're going to have here year, beginning, or beginning balance for that particular year, interest, principal, payment, and then ending. And like I said, you can do this for any loan you have right now. So year one. I hate the keyboard on my laptop. 1, beginning balance is 5,000. Now, when you have an interest only, or an interest and principal, or a fixed payment that's a payment for principal and interest, the first thing you have to do is calculate the interest for the period, because the first part of the payment always pays for interest. So I'm going to take the amount in B3 times 0.08, and it's annual, so that's my annual interest is 400. Now, since my payment is fixed, 1509.60, I'm putting that in there. So how much of this payment is applied to the principal? Well, the payment is in E3. I'm going to subtract the part that first goes towards interest, C3. So my principal will decrease by 1109.60. Going into the second year. I didn't do that. My computer's doing that. So, there we go. The beginning balance of my loan in year 2 is the ending balance in year 1. So F3 multiply B4, my new beginning balance, times 0.08. That's how much, and I'll round that so that it's dollars and cents. Oops. My payment is still $1509.60. So my principal, how much of that loan amount, E4, is towards interest? Or subtract the part that is towards interest, because that's the first part that gets paid, interest. So the remaining part of the payment is applied to the principal. So I'm going to now subtract B4, beginning balance, minus the part of this payment that was applied to the principal, D4. And that's my new balance. So I'm just going to do the rest of this so you can see. Going to now take the new balance, F4, multiply that new balance times 0.08, get my interest, going to make it so it's cents. My payment is $1509.60. The first part of my payment goes to pay interest. Oops, I'm putting it in as a cell, so plus E5, subtract the interest because that gets paid first. And that part decreases my loan amount. That's the part that is applied towards principal, B5 minus D5. So that is the new balance in my loan. So F5, I'm going to use that new balance to calculate this year's interest plus B6 times 0.08. Make that into a dollars and cents. My payment is $1509.60. E6, my payment minus the part that goes for interest, C6. Look at that, I'm a penny off. So B6 minus D6, 2 cents off, penny off. And that's just because of rounding. But I wanted to walk you through when you have a constant fixed payment, you first determine the interest based on the balance of the loan as of the beginning of the period. That is first taken out of the payment. Interest is paid first out of the payment, and then the remaining is applied to the principal, and that principal application decreases the amount of the loan. And this is how most of our loans are, like your mortgage, your car loan. personal loans. Most loans through the banks are created this way. So I'm going to go back and share my screen. I can find my PowerPoint. All right. Go back to my slides. All righty. Finally, what is a firm worth? Conceptually, it should be worth the present value of its cash flows. But the tricky part is determining the size, timing, and risks of those cash flows. Okay, so we will be looking in the future at assessing and determining what a company is really worth. And it could follow that net present value calculation like we looked at in the very beginning of this discussion. Now, it references, you can solve time value problems, and that's what this chapter was on, using our formulas. Also, in the back of your book, there are tables for present value, future value of 1, which was when you have one amount today and you want to know what it is in the future, or when you have one amount in the future and you want to know what it's worth today. There's also for annuities. So you'll see those in the back, table in the Appendix A. Also, in the back of your book, there is guidance in Appendix C on how to do computations using your calculators. And then, if you like Excel and you're familiar with it, you also have that option. So many different options on solving these different time value of money problems. So if you have any questions on any of those methods, please let me know. So there's a little quiz here, but we're going to finish off our discussion here. I know it's a long one, so you probably want to do this in pieces, but this is time value of money. Please post your questions to the discussion board.